Hi, and welcome to Allen High School's discussion of thermochemistry at the 10th grade pre-AP or honors chemistry level. We're glad you joined us. This is kind of a cool section of thermochemistry because in this segment we get a little taste, shall we say, of how a scientist would determine how many calories are in a food product. So I wish we were doing Butterfinger bars, but we're just going to do sugar to start with and then gasoline. So we have a little bit of a comparison. Now, that technique that we used is called calorimetry because it was used to determine the calories. Now, when we think of food calories, it's a little bit different than a science calorie, and we'll see that in just a minute. But what we're looking at with the calorimeter in general is we're looking at the heat exchanged. So often it's the heat exchanged between a process and water. And in this case, sometimes they're done at constant pressure, sometimes at constant volume. This is a constant volume process. In class, we're going to do a constant pressure process. And in a calorimeter like this, we would have the sample or our food or our, energy, maybe it's some sort of hydrocarbon that we're going to burn. This is isolated. So in this case, my system or where my reaction is occurring is isolated from the surroundings. And in a combustion, heat's released. Combustions, you should know that a combustion is exothermic. So it's going to release heat to the water. Now, it also releases it to the components of the calorimeter itself, but we're going to ignore that heat. So we're going to assume that there was no heat absorbed by the calorimeter, just by the water. All right, so we can focus, simplify a little bit. So it's a first step towards understanding much more complex questions. And the mathematics we've seen before. We're going to use MCAT. So in this case, we have a 0.303 gram sample of sucrose. That's actually a fairly small amount of sucrose, and we're going to burn it. So the heat of combustion of our sucrose is going to be equal in magnitude, but opposite in sign to the heat that is absorbed by our water. Now, the trickiest part here is students are tempted to use this mass in the MCAT. Don't. We're measuring the heat of the water. So we need to use the mass of the water. So the mass of our water is 240 grams. Our heat capacity, it's going to be given to you. You don't have to memorize this, is 4.184 joules per gram degrees Celsius. You may see this in Kelvin because a delta T is the same in Kelvin as in Celsius. And then it's going to be our initial temperature, our final temperature, I misspoke there, minus our initial temperature. Okay, so it's always final minus initial. There's only one time where it's not, and you won't see that until you're in AP or IB with me. So it's final minus initial. So Q of combustion, if you do that algebra, and we should get a negative number because you should know combustions are exothermic. And so an exothermic would give us a negative value, and it's negative 5.04 times 10 to the third joules. Now, that's kind of hard to picture. You see a number times 10 to the third, and it looks like it's a massive number, but it's not really a massive number. Let's put it into something with which you're familiar. Let's take a look with what this would be if we were to do it in food calories. So let's see the food calorie calculation. We would give you these conversion factors, so you don't have to worry so much about that. I'm just going to look at the magnitude because we talk about food calories in a positive sense of how much calories we would have to burn in order to burn off that food. So let's see how much exercise we would have to do. Okay, so we've got this many joules, and we're going to first get joules into calories. So 1 calorie is 4.184 joules. Now a food calorie, and you'll often see it with a capital C instead of a lowercase, is actually equivalent to what we would be familiar with in our class as a kilocalorie. So I want to get rid of calories, the little c calorie, and go to big C food calories, aka a kilocalorie, and that's 1 over 1,000. And if we do that math, we find that teeny bit of sugar. I keep thinking of Mary Poppins for some reason. Just a spoonful of sugar makes the medicine go down. So maybe this spoonful of sugar makes the medicine of chemistry go down a little easier. Okay, so we have 1.2 calories, not so much. It looked like a big number because it was 10 to the third, but it was actually a relatively small number. Now, let's take this a little bit further, because that was for, 0.303 grams. We just don't report numbers in per 0.303 grams. We want to report numbers in a unit that is relative to something, a little simpler to deal with, a little more common units. So the most common things you're going to see is you may see it in kilojoules per gram, in which case we'd have to divide out those 0.303 grams. I don't have that number, but let me just set it up for you. That would have been minus 5.04 times 10 to the third joules, and we would have to divide it out by that 0.303 grams. It doesn't ask us this, I'm just showing you this. And we'd get minus our value in joules per gram. So there are times you'd see numbers reported like that. This question is asking us to get to the mole, because we know that mole is the heart of chemistry. So let's take a look at that math. Now there's a couple of ways you could do this. I'm going to do the first one in steps, and then I'll do the second one as one long dimensional analysis. So you can pick how you want to do it. So step 1, I'm going to convert those grams to moles. Mass to moles, use molar mass. So I would have 342.34 grams. And that, if I did my algebra right, you always double check that. We can all slip our fingers on those calculators when we're in a hurry. I think I've got it right, but I know one of you will tell me if I don't. All right. So that's our moles. So then our second step would be to divide our joules by moles. And I want to make sure I keep that negative with me, because you might want to make sure you report it as a negative value to communicate that it's exothermic. So I'm going to get joules per 8.76 times 10 to the minus 4th moles. And that gives me 5.69 times 10 to the 6th joules for every 1 mole once I've divided that out. And now the third step is, you should be very familiar with that. We have to take that, and I'm not even going to do that work because I would really hope you could do that by now. 5.69 times 10 to the third kilojoules for every 1 mole of sugar. And so that's the type of number that you would see reported in books and so forth. Okay, now we are going to, for this one, it says there's one more question down there. For the combustion of sugar, do you think heat would be listed as a reactant or as a product? So which side of the arrow would you put it on? Well, combustion releases heat. We saw that the temperature of our surroundings increased. We found that our answer, and I better carry that through, naughty, naughty me. We saw our answer, oh, Dina, right? We saw our answer was negative, indicating exothermic, so our heat would go on our reactant side of the arrow. And if we were to draw a potential energy curve, our reactants would be at higher activation energy, potential energy than our products would. And it would be exothermic. So all those variety of ways of communicating. So we want to do another couple problems, and we'll do that in the next video. So until then, this is, as always, signing off.